Okay, gentlemen, continuing on with 5.4. On example 7, we want to rewrite each of those expressions in terms of capital A, B, and or C. We're working with log 2s, log 3s, and log 5s. So if I start with A there, 7A, 6 we know is equivalent to 2 times 3. So I can rewrite, if I get my pen working here, I can rewrite this as the log of 2 times 3 instead of 6. And from our properties we were just discussing, single log product is 2 log addition. We add our exponents when you're multiplying with a common base. So I can think of that as the log of 2 base b plus the log of 3 base b. And log of 2 base b is big A, and log of 3 base b is big B. On example 7b, the log of the cube root of 0.4 base b, well, I could rewrite that as 0.4 is 4/10 or 2/5, and cube root is 1/3 power. And we know that if you have the log of a quantity to a power, that power can come down in front. So I'm going to rewrite that as 1/3 times the log of 2/5 base b. And a single log quotient is equivalent to 2 log subtraction. So we can think of that as 1/3 times the quantity of the log of 2 base b minus the log of 5 base b. And we can go back now and substitute for those two quantities, and we are left with 1/3 times a minus c. Or if you prefer, 1/3 a minus 1/3 c. Either would be acceptable. They are both correct. And on the last one here of 7c, well, 15 we could think of as 5 times 3, but we also want to notice that this is a base 3b, and all of these are base b. So we should do a base change and switch our base 3b to a base b. And recall to do a base change, that would be the log of 15 to whatever new base we want. In this case, I want to work with base b, divided by the log of the original base, which was 3b, to that new base that we want. So this and this are equivalent. All we did is do a base change from base 3b to base b. So now in our numerator, 15 is 5 times 3, so we can think of that as the log of 5 times 3 base b. And in the denominator, we already know that that is 3 times b. And single log products, you are multiplying when you add your exponents, or when addition of exponents was going on. So the numerator we can think of as the log of 5 plus the log of 3. Both of those were base b. And in the denominator, that would be the log of 3 base b plus the log of b base b. And now if we go and we make substitutions for each of those terms, the top left, log of 5 base b is equivalent to c. The top right, the log of 3 base b is equivalent to b. Bottom left, log of 3 base b is equivalent to b. And bottom right, the log of b base b is equal to 1. On number 8, we want to expand those. So we're basically just doing the opposite of what we did on example 6. On example 6, we took those long expressions and we simplified so that we only had one word of log. Now on example 8, we want to do the reverse. We want to expand those out so that when you are taking the log, there are no products involved, no quotients involved, or no powers involved. So if we start with A, we have a single log quotient, and we know a single log quotient is equivalent to 2 log subtraction. So that would be the natural log of x squared minus the natural log of 1 plus x squared, and we know square root is the same thing as 1/2 power. And recall, anytime you have the log of a quantity to that power, you can bring those powers down as coefficients of those logs, because that means power to power, we should be multiplying those quantities. So we can then expand that down to 2 times the natural log of x minus 1/2 the natural log of 1 plus x squared. And now we are taking, there are no logs of any products, quotients, or powers involved. We only have the log of a single term here and the log of a sum here. So we would be done, and this would be our final answer. If we look at B, we have a single log quotient. We don't want to have logs of any quotients, so we need to expand that out. And we know that if we have a single log quotient, we can think of subtraction. Subtraction of exponents would be taking place. So I'm going to come over here to the left. So I would have the natural log of 4 minus x squared, and we know square root is 1/2 power, minus the natural log of the quantity x minus 1 times that x plus 1 to the 3/2 power. Over here on the left, the log of a quantity to an exponent, we know we can bring that exponent down as a coefficient and multiply those 2 powers. Over here, we know that a single log product is 2 log addition, so taking care of both of those at the same time, I'm going to have 1/2 the natural log of 4 minus x squared minus the natural log of x minus 1 plus the natural log of x plus 1 to the 3/2. And now again, we have another power, log of a quantity to a power, that we will be able to bring down in front as a coefficient to multiply those. We also have this minus sign that we can distribute to each of these quantities. So if we take care of both of those, our next step would be 1/2 the natural log of 4 minus x squared minus the natural log of x minus 1 minus 3/2 the natural log of x plus 1. Here we have the log of a sum. Here we have the log of a difference. But here, natural log of 4 minus x squared, keep in mind that 4 minus x squared is the same thing as 2 plus x times 2 minus x. So we technically have the log of a product. And we know that we don't want to have any logs of products, quotients, or powers in our final answer. So a single log product, we can expand that now to 2 log addition. So we would have 1/2 times the natural log of 2 plus x plus the natural log of 2 minus x minus the natural log of x minus 1 minus 3/2 the natural log of x plus 1. And if you wanted to distribute the 1/2 to each of these, you could write 1/2 natural log of 2 plus x plus 1/2 natural log of 2 minus x minus the natural log of x minus 1 minus 3/2 the natural log of x plus 1 as your very final answer. Okay, on number 9. 9 is very similar to what we just did with our A's, B's, and C's on number 7. We're just now working with natural log. I'm going to let you do I'll let you do A, and I will jump down to B. So keep in mind here, we have the natural log of x to the fourth, so we can bring a 4 down in front here. Over here, it's the entire quantity cubed. So if I want to think of the numerator, I could think of the numerator as I have something, that natural log being cubed, minus, if I were to bring the 4 down, minus 4 times that something. So let me come down and we'll expand it and we'll kind of go back to that thought process here. So in the top left, I have the natural log of x being cubed minus 4 natural log of x. In the denominator, we have here a single log quotient, which we know goes to 2 log subtraction, so natural log of x minus the natural log of e squared. Here we have a single log product, and a single log product we know goes to 2 log addition, so that's the natural log of x plus the natural log of e squared. And if we simplify each of these, the natural log of e squared, this is just 2. So in our denominator, we're really just looking at the natural log of x minus 2, and this is the natural log of x plus 2. And up above here, keep in mind, if we think of that as our natural log of x, like a big old A, we have something being cubed minus 4 times that exact same something. So in our numerator, we could be factoring out that natural log of x. If I take out that natural log of x, I'm going to be left with the natural log of x squared minus 4, or that's going to be the natural log of x times the natural log of x plus 2 and the natural log of x minus 2. And this was our numerator, this was our denominator, and we can see that our natural log of x minus 2's are going to cancel, our natural log of x plus 2's are going to cancel, and the only thing that we are going to be left with is the natural log of x, and the natural log of x was equal to t, so our final answer is just t. On 10, we want to express those in terms of natural log, so now we're just going back to our base change. On A, keep in mind, base 10 is implied, and if we have 2 log division, that implies a base change. So I want to switch to natural log, which means base E, or ln. And so now the log of 6 base 10 would be the same thing as the natural log of 6 divided by the natural log of 10. On B, we have base 2. We want to switch to natural log, base E. So the log of 5 base 2, if I do a base change, would just be the natural log of 5 divided by the natural log of 2. And on example 11, our last 2 here, we want to solve for x. On A, I'm going to divide both sides by 2, trying to isolate that term that has the variable that we are trying to solve for. So right now we're looking at 5/2 is equal to e to the 2x minus 1. And recall, we are looking here at an exponential form, so we can switch this to a log form. And in our log form, recall that logs are equal to exponents, and the exponent on our exponential form was the 2x minus 1. So our 2x minus 1 is equal to the natural log, because we are working with a base of e here. So the natural log of 5/2, and now we are able to isolate our x variable here. So if we just add our 1, and then we divide out our 2. And then that would be our final answer for x. Last one here, 10 to the x equaling e. We are looking at an exponential form. We can switch it to a log form. Logs are equal to exponents. Our exponent is the x. We are working with a base 10 here. So we are looking at log base 10 is implied of the log of e. And so that would be our final answer for x here. And we know that if we are looking at log of e and we want to switch this to natural log, because right now we have log base 10 that is implied. So if I want to switch that to natural log or log base e, then that would be the natural log of e divided by the natural log of 10, and the natural log of e is just 1. So our final answer would be 1 divided by the natural log of 10. And that is it, gentlemen.